Okay, for the next one, it is the particle swarm optimization. So open the notebook here. We look at the general of the particle swarm first. Okay, so this one is the general idea of particle swarm, and you can see that I use the class of bees instead of calling it the particle. I call it bees. So this one is a class of bee, and our initial term is, can you remember? We have the omega to be the initial, and C1 and C2. C1 and C2 is the one that, sorry, I would like to swap. I would like to swap to our node again. Okay, so okay, so you can see that we have the term initial here, omega. So I declare omega C1 and C2. Okay, in term of this. Okay, and then this one is the constructor. So our constructor is like super simple. Just store everything in x, y. This is the position vector, and vx, vy, the v vector, and px, py, the local based vector. And I save everything, every point that this be moved. So I'll keep it here, and the marker and the color is here. So to move it, I have to calculate the new v. The new v can be calculated using the v from last iteration times the initial plus c1 times random times p minus x. Okay, and then plus c2 times random times gx minus x. Okay, so this is the same as in our equation. We have new Vt to be omega of Vt minus 1, right? Right? And then plus C1 R1 P minus X, this vector. Plus C2 R2, and this one is G global base minus X. So this is the equation of updating V. So I I or spread it into X and Y axis. And then, as I told you that the vector V is like the movement of each particle. So once we can calculate V, we add it to X and Y directly. Okay. And then add the X and Y of this position to the trace. X, Y, but for the C1, add it with the fitness. Okay. For the fitness one, I use the space of this one is quite simple math dot this one. This is the mountain X and Y, X and Y. I think you can see that for I calculate the fitness using this function. Using this function sine x squared plus y squared divided by x squared plus y squared. So it is this one sine of x squared plus y squared divided by x squared plus y squared. Just the simulated fitness. Just the simulated fitness. Okay. So to update the update G, I will iterate through all B's, and then if B.fitness is greater than G and Gx and Gy, just set Gx and Gy. That's all. So I start B's to be like random B that scatter from minus 10 to 10, minus 5 to 5, and then store it here. Okay, and do it 5,000 round, and this is the result. I will. You can do it also. You can copy it and run it in some other place. I will run it in another Python one.อันนี้มันไม่ได้ช้าพอไม่ได้ช้าเพราะซูมนะครับน่าจะช้าเพราะเครื่องสเต็ปขนาดนี้ Okay, finish. So you can see that I use 5 B's and all of them, you can think that this one is like a mountain, and you can see that the bees move. All 5 bees, they are like we are lucky that all of them is on some sides of the mountain. so it cannot move. So it can fall like not the best one, but some place that is you can think that is like the hill, the ring of the hill. This one is like it merged at the 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 mountain ring before the best one. Okay, so you can try to run it again. Yep. So this one, you can see that it all bees now, they are at the top of the mountain, of your mountain. I'll try to change some value first. I will change C to some a little bit lower values, to 1.5 or 0.1, 0.1. Let's look at the result. This one. So all of them like share the going to the top of the mountain. Same. Okay. Look at this. I will change it to value that is like lower. This one, because now C1 and C2 is very low. So every movement is quite very small steps. So you can see that it's like the trace of your piece. And this is your result. Okay. So you can see that each B is like, this one is the space of X and Y. So you can see that each B is like, it is moved like it owns somewhere. And then once some bees has the once some bees like found the better global, most of them for the remaining bees, it will try to join. Okay. So you have to change this and try by yourself if you want. C1 is go back to themselves, and C2 is go to the global one, right? So if you make it like, okay, change C2 to be very low and C1 move it back to its local base, what happened? Can you see? It doesn't merge somewhere. Can you explain the result? Why? Because we set C2, that is the coefficient of moving back to global, moving to global base. We set it to very, very low value. So it doesn't merge. They don't merge because they don't move to global base. Okay. And if you change it to something else, that is, don't move to local base. Don't move to local base. Try to move global base. What happened? it will like go directly to global base. Can you imagine that some the all 5 Bs we have common global base, right? So each B try to move to the best place that someone found. Okay. So that is try to move to the global base. So maybe if we use this method, it may like not merge in the best place. Okay. Okay, for the particle swarm, do you have any questions? You can try to run it by yourself. I've already written the code here. And I have the particle swarm for n queens and particle swarm for linear regression also. This one is particle swarm for n queens. Look at this. I didn't write the code to show on the screen because it's quite very difficult to show 16 dimensions, right? And I just print the global base on the screen. This one is the first generation, and then this is the first generation. The global base is 11, and then I print every. I think I print every 1,000 or 10,000. I'm not sure. I print every 5,000. Every 5,000 iterations, I will print the all informations of the bees on the screen and also the global based one. So let's wait and see the result. So you can see that we randomly generated n particles. Oh, I'm not sure how many. Oh, this one is at 5,000 iterations. At 5,000 iterations, we found global base here. Wow, it's just only 3 pairs of 16 of them. That is like okay, at 5 at 10,000, the one that still found is the best with 3 pairs. Okay, so I'd like to stop this one and you can try by yourself later. Sometimes you can find the best one, sometimes you cannot. And for particle swarm for linear regression, or as you can see, GA can find, right? GA can find very good results. So this one, MSO, CSO, too many sessions. Sorry. I have to stop this one first. Okay, our MSO and CSO is here. And just check this. This one, so you can see that your bees is like each bees got very high error here, very high error, and it. So at the first iterations, global base is now is yep, it's become lower 500. Your global base is better and better. So you can see that I print every 100 iterations, and so it becomes like lower and lower. Okay. And this one is like movement of your bees. Okay, so all of them join. This is the surface here that the lowest one should be around there here. Okay, so all of your bees try to move together. So I hope that you can adjust the parameters. If C is too high, what does it mean? It means that your bees will move one step very far from the previous one. So you have to lower the value of C. Okay. Okay, so I hope you enjoy it and see the result of the code I've written by myself. So maybe I think you can improve it. You can try to change. Okay. So do you have any questions?